Hello guys, welcome to our channel. So to deal with this particular problem, we are being asked if the spherical polar coordinates r, theta, phi are y, which is equal to r sin theta cos phi, z, which is equal to r sin theta sin phi, and w, which is equal to r cos theta. Find an expression for a volume element in the coordinates. Now, in other words, we are being told to look for the Jacobian of this particular problem. First thing first, you need to represent this particular problem in form of Jacobian. So we have that j of r, theta, phi is equal to. Now you need to look for the differential of the first function y with respect to r. We look for the differential of y with respect to r, differential of y with respect to theta, differential of y with respect to phi, the same thing with other functions. So first we have the y over the r, then we have the y over the theta, next we have the y over the phi, so moving to the next function, we have before we proceed, you need to look for the differential of y with respect to r. Now we need to represent all of this into this particular place. So therefore, we have the Jacobian r, theta, phi to be equal to, for the y over the r, we have sin theta cos phi, and the y over the theta is r cos theta cos phi. Now next to the third one, we have the y over the phi, which is equal to negative r sin theta sin phi. So now the z over the r is equal to sin theta sin phi, the z over the theta, so the z over the r, y the z over the theta is r cos theta sin phi, and the z over this phi is equal to r sin theta cos phi. Now for the w over the r, we have cos theta, and for the w over the theta, we have negative r sin theta, and the w over this phi is equal to 0. Now the next thing to do is to look for the determinants of this particular matrix. Now you should know that whenever you're looking for the determinant of a matrix, of a 3 by 3 or any other n by n matrix, we have positive, negative, positive, negative, positive. Let's say for a 5 by 5 matrix, so we have negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, just like that. But for a 3 by 3, you would have positive, negative, positive, negative, positive, negative, positive, negative, positive. So this would be for just this 3 by 3, meaning that the coefficient of this particular place will be positive, here will be negative, and here will be positive. Now in order to look for the determinant of this particular matrix, whenever you are taking the determinant, you can take the determinant from here and then you still get the same answer. You can take it from here, you get the same answer. In fact, you can take it from anywhere to get the same answer. But today, I'll be making use of these particular ones to get my answer. Now, looking for the determinant of this matrix, I have the determinant of the Jacobian to be equal to Now when I map out this particular entry, I map it out because it is being found in this column and also in this row. Now what is being left out are this particular entry. So we have cos theta. So I have here r cos theta cos phi negative r sin theta sin phi r cos theta sin phi r sin theta cos phi. Then I come down to this place. Now remember, negative times negative, it gives us positive. So I have here 3 plus r sin theta. Now when I map this out, I'll be having this to be the entries that have been left. So I have here sin theta cos phi negative r sin theta sin phi sin theta sin phi r sin theta cos phi. So we have cos theta. Looking for the determinant of this matrix, we therefore have r square sin theta cos theta cos square phi. Now minus, because of this negative here, it turns towards positive. Now looking for the product of these two, we then have r square sin theta cos theta sin square phi. Now that is that for that. Now move on to r sin theta. Now when we look for the determinant of this matrix, we have r sin square theta cos square phi minus, but because of this negative here, we have positive. Now plus r sin square theta sin square phi. So let's continue. Now by factorization, I can notice that r square is common here, and also sin theta cos theta is also common here. So by factorizing, I have r square cos square theta sin theta. Now when I factorize this from this, I have left cos square phi. And when I factorize this from this, I have plus sin square phi. Now moving on to this, I can factorize r sin square theta here. So by factorizing r sin square theta here, I have r sin cube theta, rather r square sin cube theta in the bracket of, now when you factorize this from this, we have left cos square phi. And when you factorize this from this, we have plus sin square phi. Let's continue. Now remember that cos square phi plus sin square phi is equal to 1. So we can see that we have r square cos square theta sin theta. Now this is 1 plus r square sin cube theta. Here we can also factorize r square sin theta here. So we have r square sin theta, then in the bracket of cos square theta plus sine squared theta. Remember, when you factorize r squared sine theta here, which is common in both ends, what is being left here is cos squared theta. And when you factorize this from this, what is being left is sine squared theta. Like I said before, cos squared theta plus sine squared theta is equal to 1. It may not be theta, it may be A, it may be B, it could be anything. So cos squared theta plus sine squared theta is equal to 1. So by replacing 1 here, we have that this Jacobian j of r comma theta comma phi is equal to r squared sine theta. If you are new to our channel, subscribe, hit the notification bell such that whenever I drop a new video, you will be notified.